So let's now move to the prove the upper bound, which I promised. And first, I remarked that the fully mixed Nash equilibrium. I'm saying there because there is only one such an equilibrium when each player puts probability of 1 over the number of machines, 1 over m, on each machine. So there is only this symmetric fully mixed Nash equilibrium. And that fully mixed Nash equilibrium isn't always the worst, as we saw on the example, but the lower bound, which it can show in some examples, in some other examples, of order of log m divided by log m, that is actually a tight bound. So that cannot be improved. Excuse me, it should not be that should not be increased. That's enough. That's a tight bound, as we now prove. The theorem is consider any load balancing game with n tasks, or with W1 till Wn, and m identical machines. So the limitation is that the machines are assumed to be identical, of the same speed, and then for any mixed Nash equilibrium, P, there holds that the social cost of this P is bounded by the order of log the number of machines divided by log the number of machines times the optimum of this instance, this log balance. Here, G is the game, not a graph or something. It's a game. So now what I want to emphasize is that O is this order. That means, if you don't remember, that there is a constant such that from some point on, the social cost is at most is constant times log m divided by log m times plus maybe some constant. So basically that's the order, and moreover, I want to emphasize that log m is already a slowly growing function. It grows to infinity as m approaches infinity, but it grows slowly, exponentially slower than linear function. And log m is an even more slower growing function, also to infinity, but even slower than log. And log divided by log, this factor, L, excuse me, this factor grows to infinity as m approaches infinity, but very slowly, slower than log. Okay, having hopefully understood the theorem, if not, let me know. Let's prove it. It's not so simple the proof. Actually, it's quite long. It's mostly technical. So, of course, try to grasp the most important steps and the logical steps. The technical things like, okay, Chernoff inequality of this form, that's less important. So just you have to understand this, but I usually just give you the inequality and then it's just a technical thing. So without loss of generality, the speed of the identical machines is just 1, and despite that the social cost, as it's defined, is the expected maximum load, we start by actually upper bounding the maximum expected load. Not the same. Expected maximum is in general always greater or equal to the maximum expected, because maximum is a thing. Maximum is a concave function. So the Jensen inequality proves that. But anyway, we just start with something else. We start by upper bounding maximum expected. What we do actually concretely prove a thing which is similar to what we proved for some other scenario for the Yuan-Nash equilibrium of also identical machines. What we actually prove here is that for any machine, the expected load is bound by 2 minus 2 over m plus 1, something smaller than 2, times the optimum. And that not only is the formula similar, but we actually adapt the proof of what we did for the pure price price of anarchy bound for identical machines. I now recall you the proof what we did then, and then I'll show you exactly what we do now. So that's the first step. I don't tell you why we'll need this to eventually bound this. And the thing that we did proof for the pure case was as follows. That's our reminder. And I said that the analysis resembles analysis of greedy load balancing algorithm. And okay, that's something which I also said then. But let's now go to what we proved and how we proved it then in this scenario of pure equilibria. So the theorem said that when a load balancing game with n tasks and m identical machines, a pure equilibrium, a pure schedule in A fulfills that the social cost, again, it's pure, is at most is bound to minus 2 n plus 1 times optimum. So basically, the social cost is, of course, the maximum, right? It's divided by the maximum load. So then we prove that the maximum load is bounded by something. Here we need to prove that the maximum expected load. Okay, let's go back. And let's see how we prove that the maximum load is bounded. It actually was a simple proof that I have 3 main steps. So let me just remind you what we did for the pure case. And that's actually good for you to maybe grind a bit more on that proof to basically rehearse that proof. So given A, let's schedule, denote by J a maximally loaded machine under A. Maybe there are several, but some maximally loaded machines. There are M such finite numbers, so there is a maximum. And let I star be a player, or a task in other words, who goes to that machine and whose weight among those who go to that machine, J star, is maximum. Excuse me, minimum. Again, there may be several such minima, but there are such because, again, there is a finite number of tasks in general, so there is something which obtains a minimum, and one of those we pick. So a maximally loaded machine and a minimum task going from those who go to that machine. Now, so far, so generality, the load of that machine is at least 2, otherwise the social cost is just 1, and it's also the optimum, so the bound which we need to show will particularly immediately false, and we are done. Now it's not, then it has to be at least 2, and then the social cost is going to be at least twice this minimal weight, so the weight is at most half social cost. That's the first step. The second step, that's why we use this idea that this assumption that A is an equilibrium. We look at any machine J and J is of course a machine. It's not plain, so it has to be in M. Not in here, it has to be M, not N. Let me fix that. You can never go for you can never find can never be sure there is no typo. Luckily this typo is not complicated. So I had this typo apparently here. But I provided this proof originally, so yeah, it's not a good idea, but so now I'm going to fix that. So okay, the second step of our proof is that for any machine, it has to be in M, in bracket of M, besides the star, that if there exists a machine which is a machine J, which load is smaller than J star, minus the weight of a minimum player going there, I star, then it cannot be y, because if they had fetch a machine, then task I would have deviated from task I star would have deviated from j star to j, and it would have strictly benefited. Why? Because we know that the log of j plus the weight of I star is still strictly smaller than the log of j star. So what I star experiences now. So I star would strictly benefit by deviating from j star, where he is now. I remind the definition of I star to j. And since A is an equilibrium, it cannot be. So the load of actually j has to be at least that. So this cannot happen. And since the load of j star is exactly by the choice of j star on social cost, the most loaded machine, and the weight of I star is at most twice social cost. Okay, now this is compiled finally. The load of I is at most twice social cost. So minus that is at least social cost minus half social cost, not twice, 1/2. We have obtained eventually that the load of j is at least half social cost for any machine j. Well, for any machine j which is not j star, and for machine j star it's actually equal, also at most. So this is the step I use the fact that A is in equilibrium. And finally, the third step, the punchline, is that since the optimum is at least the average load, what we get? Now, the optimum, why is it at least the average load? Because the optimum is the maximum load, definition. And maximum load is simply at least the average. Now, the average load is at least, I mean, the sum divided by number of machines, the sum is at least the social cost, because one of those is exactly the social cost, the L of j star. And each of the m minus one other load has the load of at least half social cost, by what we've shown here. And so we have this bound, and then we just multiply by 2m divided by m plus 1, and obtain the bound of social cost is at most 2 minus 2 divided by m minus 1 optimum. Now, that's the third step. The third step, and that's how we proved the bound, the social cost of pure scheduling is at most 2 minus 2 over m plus 1, the optimum. That's what we did. Now we need to extend that, to generalize that, or let's say to adapt, formally speaking, and to prove the same for the expected load of any machine, not for just load, but for expected load. And we assume also that the scheduling is some mixed machine. Okay, so what do we do? Very similar, not much harder than what we did now. So we just do the following. We start by proving that for any machine, as I said, that's what we do. The expected load is at most that 2 minus 2 over m plus 1. I already remember this number. Times the optimum. Now, given P, which is assumed to be a mixed Nash equilibrium, the first step, I remind you what we did there, was proving that the weight of this I star is at most half social cost. Otherwise, we would have something which is already done. Yeah, we divide J not to be just the machine with the largest load, but the machine with the largest expected load. And I star is not, that was the J star, then I star is not just a player. When I said J, the machine, it's wrong. It's a machine with the largest expected load. There may be several. I star is not a player with the smallest weight, which goes to that machine, but rather a player with the smallest weight, which goes to that machine with a probability. Okay, with a non-negative probability. This probability has to be at least zero. Excuse me, greater than zero. So basically, that machine is in the support of that. Is in the support. That player strategy. So that has to be strictly greater than zero. Now, without loss of generality, the that's the first step now. The expected load of the J star is at least 2, because otherwise J star is the maximum, has the maximum expected load. If expected load is strictly smaller than 2, then the maximum is strictly smaller than, is at most optimum, and again they're done. So we can just assume it's at least 2. And then, since the expected load is E I star J star, the probability with which I star goes to J star times the weight of I star plus something. So this E I star J star times the weight of I star is one of the non-negative summands in the expected load of J star. So that at least actually twice that thing, because because I is chosen to have this minimum. Yes, that's going to be twice. Actually, 1 second, please. So I actually have added something I forgot to write. I star is defined to be the minimum, not just a minimum weight, but rather weight times the probability. Among all those who go there, among all those who have J star in their support, the one with minimum Pij star times the weight, or A1, the minimum, is I star. Now, just the expected load of this J star has to be at least 2. Otherwise, this inequality holds for sufficient enough M, for large enough M, and we are done. Since it has to be at least 2, it means that in particular, since I is a minimum among those who are there are at least 2 such, at least 2 such, then we actually can tell that twice the minimum has to be bounded by this expected load, and therefore this value is at most half of the maximum expected load. Okay, so I've made another typo, my apologies. And actually the typo was originally in the original proof. So the original proof was wrong in the following place. Without loss of generality, the number of those who go to J star is at least 2, not the load, because the load is the total weight divided by the total the speed. The speed is 1, so just as total weight. It's not the same as the number. The weights are not guaranteed to be 1. The speeds are 1. So that's not the same. The number of those who go to J star is at least 2, because otherwise it's fewer at the original proof. So otherwise it's just one person goes there, it's simply optimal. Then we are done. And then we continue as before. Now in the new proof, I did change a bit. I did deviate a bit from what I say in the book. I think either they're wrong. I don't see how they're right, but in the new proof, that's what we do. So from the start, let's just do it from the start. I apologize for the confusion, but it's because of the book given only as a sketch. It's actually good that we work this out, kind of an exercise we're doing. So given a mixed Nash equilibrium P, we define J to be a maximally loaded machine in expectation. Then we define I star to be a player which has this machine in his support, and that's the difference on the book, which has them among those players having the machine in his support, not having the mass just the largest weight, but the weight times its probability is the largest. Now, the outcome of generality, the number of those who have the machine in their support is these two, otherwise, as before, it's going to be at most optimum, then maximum, and then we are done. Now, since there's at least two, and this is I start chosen to have the minimum weight, there are at least two such, and therefore twice Pi star J star times Wi star is at most maximum weight. So that's what we have. That's the first step. I apologize for your confusion. Second, the second step, I remind you, was using the fact that we assume that our schedule is in equilibrium. Here we assume it's a mixed equilibrium. To bound this from below, what we did before is that we bounded the load on any J star from below by half of the social cost. And what we do here is that we do a similar thing. So for any J, which is not J star, if someone has an expected value strictly smaller than what J star has, minus this contribution of I star, so the probability times the weight, then and before I star would strictly benefit by moving from J star to J. And since A is a mixed Nash equilibrium, that mix on scheduling is a mixed Nash equilibrium, this cannot be. So this cannot be, it has to be the opposite sign. So for any machine otherwise than J star, the expected load is at least that of J star minus Pi star J star times the weight of I star. And now, well, the expected load of J star is exactly equal to the maximum possible expected load by the definition of J star. And this is, as we have seen here, is at most half of the maximum expected load. Therefore, minus this is at least minus half the maximum expected load. So eventually, it's half the maximum expected load. And that's for any machine other than J star. For J star, it's trivial. So for any machine. So for any machine, the expected load is at least half the maximum expected load. And then the third step, that's the punchline. That's also similar to what we did before. Well, see, it's not hard, but it's a bit confusing. 1 second. So the punchline is as follows. Since the optimum is at least the average load, we get that, okay, the optimum is the expected, let's go step by step, is the expected maximum load. It's not the maximum expected, it's the expected maximum. That, in turn, is at least the maximum expected, which is simply at least the average of the expected load. Maximum is at least the average. Arithmetic. Now, the arithmetic average can be bounded by from below, lower bounded as before. So 1 is the maximum, and the rest are minus 1, and at least half the maximum as we've shown before. Yeah. In the second step. And then we obtain that, and then we just obtain that optimum is at least m plus 1 times the maximum divided by 2m. So the maximum is at most 2m divided by m plus 1 times optimum, which is at most, which is equal to 2 minus 2 over n plus 1 of 2. And we are done. So let's after having this long detour, lemma, let's go back and see what we need. So we assume that the machines are identical, and we assume there is a mixed equilibrium. We need to prove this bound. Now, we said that, and despite that, the social cost is expected value of maximum, is the expected value of the maximum, we start proving that there is this bound on the maximum expected value. And that's what we've done by adapting the proof on the way we found in the type window. Now going forward, we continue to prove what we need actually. So that's what we've done. Now, as usual, I try to remind you in the long proof what we did before. We haven't proven that for any machine J, log is at most 2 minus 2 over n plus 1 of the optimum. Then I'll prove that the expected of the maximum, the expected value of the maximum is at most what we need, is O log m divided by log m. And we use the following weighted Chernoff bound. So as usual, Chernoff is some bound on the deviation of some independent random variables value. But we don't prove it here, we just use it. So given independent random variables x1 till xn, whose values in the segment 0 to z, or some positive z, define x as their sum. That's also a random variable. Then for any positive t, we have that the probability of these at least t is bounded by the number e, the base of the natural logarithms times the expected value of x divided by t, everything to the power of t over z. That's the bound. No, don't go into why that's just what we have, some bound on deviation from t on when the sum is at more or less t, the sum of independent random variables. Now let's go to what we do here. So for j, be in a machine, divide w to be the maximum weight among the players, and for any positive t, the Chernoff bound above applied on the indicators. Now I remind you the indicators x, I, j. These are one if ai goes to j and 0 over. That's a random variable indicator of as pure scheduling. Now we can see our scheduling as a mixing of pure scheduling, and therefore we can see basically the Lj, the load on machine J. I remind you, what does it mean? It means that the load on machine J is the sum of the weighted weight, so probability times the weight, divided by the speed. The speed here is 1, so just the sum, the probability times the weight. Now, these probabilities are independent, and therefore the independent random variables with values in 0, the maximum value is probability 1 times the maximum weight, W. That is W, can be taken W. And then you see that the lot being the sum of those variables. I remind you again, the variable here is the weight times the xij. The weight of I times xij. Now the probability of this x, in this case Lj, being at least t for any number t by this Chernoff bound is at most e times the expected value of x divided by t to the power of t over z. Now first of all, probability is bounded also by 1, that's why I can say it's minimum between 1 and the bound we have from the Chernoff bound, which is the basis of natural logarithms e times the expected value of x, j, divided by t to the power of t over z is w, as I said. Now we can bound that expression in turn by the expression 2e optimum divided by t to the power of t over optimum y, because the expected value of the load is at most 2 minus, that's what we're proving, 2 minus something times optimum, at most 2 times optimum. That's why we can just replace expected value of load by twice the optimum. And the optimum, of course, at least the total, the maximum weight. And therefore, the power of optimum is at most the power of something divided by the maximum weight is at most the power of t divided by optimum. So we replace this and w by optimum. So that's what we have got. And well, we need to prove that. That's a reminder. So for any machine, and defining w to be the maximum weight, we've shown that for any t, any positive t, that's what we have for the load. The probability of load being at least is positive. Now define tau to be twice the optimum times ln m divided by ln m. Then for any positive number x, for large enough numbers m, and fine to go to large enough because we talk about the order O, capital O, we have probability of Lj that greater or equal to tau plus x. Now we have some expression for any number t, in particular for this tau, we've defined plus any positive and non-negative x. We can substitute the value for tau here, and we get that. Now, then we can bound that from above using the following inequalities which work for large enough m. Now, log m divided by log m is at most square root of log m. Therefore, e times log m divided by log m, so e divided by that thing, is at most 1 divided by log square root of log m. Now I forgot. One second. Okay, so there was another typo, and that's now I fixed that. Here, for large enough m, we have this bound. Log m divided by e ln m is at least square root of log m. So here we have the opposite, the 1 over. Therefore, it's at most 1 divided by square root of log m here. So the expression extended inside the parentheses is bounded by that. And now we have this to the power of 2 ln m divided by ln m. And then we have this same times the same to the power of x divided by optimum. Now we can actually bound again what we have in the parentheses by e from below. Therefore, 1 over is going to be bound by e from above. From 1 minus e by e to the power of minus 1 from above. That's why we can bound this by that. E to the power of minus x divided by optimum. So using those inequalities, which are just put in for large enough m, what we have, we now have that it's a continuous flavor state expression, and we have it at most m to the power of minus 1 times e to the power of minus x divided by optimum g. So we've managed basically to bound this probability. Now we are almost done. Now recall that for a non-negative random variable, the expected value of that variable can be expressed using this integral. And then the social cost, that's what we now need to write to bound from above. The expected value of the maximum load. Social cost is the expected value of the maximum load. It can be seen as the integral of the maximum load, at least t dt. Here we have a reminder what we did. Here, social cost, so the expected value of maximum load is equal to the integral. Now, recall that t is equal to, just use a substitution. So divide some tau, 2 optimum time ln divided by ln m. And for any x, we use that tau plus x as t, because we knew something for any t. So basically, we can change the variables, and then we'll get the social cost is at most what? Now, the probability of something being at least t, now is going to be at least tau plus x. Not at least t plus x. Not at least t plus x, but at least tau plus x. dt remains the same because dt and d tau, sorry, dx is the same because tau is not a function of t. The only thing we can change, which can change because of this change of variables, is that the limits of integration can change by tau. Now the integration is of something which is at most 1, the probability. Therefore, the value can grow at most by tau because of this change of the limits of integration. So the social cost of p can be bound from above by tau plus the integral of that. And here it has to be tau. As I said, it has to be tau. Yes. So now the integral of the probability of what it means that maximum is at least t. It's the same as saying that is either J1 is L1 is at least t, or L2 is at least t, or L3 is at least t, and so on till Ln. Now it's done. Now, so these are events which may intersect, but the event maximum is at least tau plus x is simply equivalent to the union of, so, or either event L1 is at least tau plus x, or L2 or Lm. And even for intersecting event, the probability of their union is at most the sum of probabilities. If they don't intersect, then it's exactly the same for a countable number or finite. But since the main set, we can just say it's at most, so the probability of this maximum is the same as the probability of either that or that or that, of the union of the event, is at most some probability. And that's what we have here. It's called the union bound, or the Boole bound. Now the tail bound above, and I mean that, for large enough m's, we have that, implies that we can bound every variable inside this sum large enough m by m minus 1 times m to the power of minus 1 times e to the power of minus x divided by optimum. So every one of those m is bounded by that, that. Therefore, we have this. The integral is simply equal to optimum. So that's what we have. Eventually, we have proven that the short cost of p is at most tau plus optimum. Since tau, and remind of how it was defined, is 2 optimum times the log m, ln m, divided by ln m. It means that we have at most ln O ln m divided by ln m optimum. And we have done, and we are done. So we have proven what we wanted to prove. Yes, we have proven what we wanted to prove. And since we already have seen that it can be at least as bad as that in the case of a fully mixed equilibrium, we know that that actually can sometimes be